Okay, so how here I've finished writing down the list of the work function phi in electron volts. Cadmium 4.07 electron volts, aluminum very similar, silver 4.73, platinum 6.35, lead 4.14. So how does this help us understand the observations? In particular, how does this help us understand, for example, this threshold frequency below which, if the light has the frequency below this, we see no photoelectric effect? Well, if we adopt Planck's hypothesis that the electromagnetic energy is delivered in chunks, uh, and that those chunks have an energy of h, Planck's constant, times the frequency nu of the radiation, then what we see is that when that energy is less than the work function, then then no matter how many photons you have, none of them deliver enough energy to the material to kick an electron out, to liberate an electron. And so we don't expect a photoelectric effect. Okay, we don't expect any electrons to be able to get out, because not even one, because no single electron has enough energy to do that. Okay, and furthermore, what we would expect is that when h nu is equal to phi, that's just the threshold. That's basically when each photon has just enough energy to kick out one electron, and so we would expect the frequency threshold to be related um, to the work function like this. It's just the work function divided by h. Okay. Now, before we go on, you may wonder why it took so long to uh, to discover the fact that light, in fact, that the electromagnetic energy is actually delivered in chunks and is not continuous. That is that you don't have a continuous delivery of energy, but rather it comes in discrete parts that have this, which are related to the frequency of the radiation by h nu. Well, maybe it helps to sort of see what the sort of magnitude is of Planck's constant. Okay, so Planck's constant h, um, in normal SI units is 6.626, plus a bunch of other numbers, times 10 to the minus 34 joules times second. Okay, so that's an incredibly small number. Okay, so if you have a frequency of light, or the light frequencies in the visible are on the order of 10 to the 15th, 10 to the 16th inverse seconds, hertz. So when you multiply those two, you still get an incredibly small number. We can write this in other units. It's also 6.626 times 10 to the minus 27 erg seconds, if you like those units better. And it's also equal to 4.136 times 10 to the minus 15 electron volts per second. So those are the kind of the typical units which we may use. And so in particular we often use electron volts, for example here, right? We're listing phi in terms of electron volts. So if you have phi, the work function, on the order of a few electron volts, okay, and the Planck's constant is something like a few times 10 to the minus 15 electron volts, then that tells you that the light frequency has to be on the order of 10 to the 15th inverse seconds, or 10 to the 15 hertz, in order for the electromagnetic radiation to be able to kick out even a single photon. Okay, so a single electron. So we now see that since these frequencies, this number, Planck's constant, so small, made it very hard to detect, basically, that light comes in chunks.